Right, that's indicated by the blue little thing there. So it needs energy to jump to a different state or level. That's a process called excitation. After some time, in terms of small little things, it could be nanoseconds, but it'll give off energy when it returns to its original state. So it'll jump up a level and then it'll go back to its normal state. And it'll give off energy. You see there, I've said E equal to hv. Right, you would have come across that in physics as well. That energy could be in the form of some sort of radiation. So we saw some pictures in the last lecture of some blue glowing around the insulator or the high electric fields. So that energy given off could be in the form of light. And maybe in HV2, where we talk about corona, we can discuss that a bit more. Right. There is a case where the molecule can get too much energy and the electron can actually detach from the molecule. So it'll jump out of all the states and it'll be a free electron and it will leave behind a positive ion. So that's the process of ionization. Right. How does this molecule get energy? It could be from another molecule bashing into it. It could be from another electron going fast enough to bash into it. It could be again from light or radiation. So again, we'll remember the macroscopic model of a gas where your pressure and volume is related to your number, density, Boltzmann's constant, and temperature. This doesn't actually help us much with what we want to do because it doesn't tell us anything about ionization or later on attachment. The microscopic model is slightly different. It gives us a little bit more information and understanding of what happens in a gas. Right, so the microscopic model, it's basically saying lots of little gas particles are in constant random motion and their velocity is related to a probability. So the probability of finding a particle at a certain velocity is given by the Maxwell-Boltzmann distribution. So that's this equation here. And graphically, if we draw it against velocity, it'll have some sort of curve like that. Right, it'll have a mean velocity somewhere. You can see it's got the mean velocity where the probability of finding a particle at that velocity is the highest. Probability of finding a particle not moving is basically 0. And the probability of finding a particle moving very, very fast is also close to 0. Right, so let's talk about some other things here. If we have some gas particles, the distribution of velocity would be dependent on the mass. Right, so an electron, which is very light, would have a different probability distribution to an ion, which is basically the nucleus of a molecule. Right. Your temperature is important. So if the temperature is higher, this curve would also change. If you think about it, the hotter the things are, the more energy there is in the system. So this curve would likely shift, this peak of this curve would likely shift to a higher value, meaning that the mean velocity of particles would be higher. The charge of a particle also influences what's going on. So remember that if you have electrons, they have a negative charge. It won't be just dependent on the mass and the temperature. Opposite charges will actually push each other away. So there will be a force there as well, and that'll change the distribution. Right. That velocity, it's also equivalent to energy. It can be related to the energy of the particle, 1/2 mv squared. Right. So going back up a little bit to this Bohr's model, we can now start looking at these movements of electrons to excited states or ionization in terms of energy. So if we have electrons in a gas and they've got enough energy all the way up here, they could clash into a molecule, pass that energy to the molecule, and an electron could jump off. How do they get that energy? If you look at just a gas, the particles will be in random motion. If you put an electric field in that gas, that electron will move according to that electric field. It'll collide into a molecule. It may bounce off, it may release an electron, it'll bounce off the next one, but generally it'll move in the direction the electric field tells it to. And that's given by the Lorentz force. Right, we spoke about ionization. It's when a neutral molecule becomes a positive ion and an electron is separated from that molecule. It occurs through collisions, photons, radiation, thermal, etc. So it's wherever something gains enough energy to impart to the molecule. There's some interesting things here. We need 12 electron volts for ionization to occur in oxygen. That's a minimum. We need 15.5 electron volts for it to occur in nitrogen. And 15.32 electron volts for it to occur in SF6. So that's an interesting thing. Earlier I told you that SF6 was a much better insulating gas than N2 or air. So now there must be something else that we need to look at later on. Right, again, that minimum energy, it's just the minimum energy required to cause ionization, but ionization may not happen. It is probabilistic in nature. So an electron could bounce into a molecule, it could impart all of the energy, it could impart half, it could impart none. So at very low pressures, gases are a good insulator, or the lack of a gas is a good insulator. So in a vacuum, there are no gas particles. There's nothing to cause a sustained ionization process. You can't ionize what's not there. So there is a different process in vacuums, but we don't quite tackle it in this course. At high pressures, there are so many particles that it actually prevents an electron gaining enough energy. Right, so again, if we look at something like this drift velocity, if that molecule is traveling through the gas, that electron is traveling through the gas, it'll collide so many times with molecules that it'll never get up to the speed or the energy levels of those to cause ionization. let's look at what they call an electron avalanche, or the process of the ionization. Let's look at a gas between two electrodes with an electric field set up between them. An electron will come in, it'll hit a molecule, it won't join that molecule, it'll release an electron from that molecule, and it will also continue on its path. That electron will gain enough energy, hit another molecule, release another electron, and it itself will carry on. The electron that we released up here will hit a molecule, it'll release another electron, it'll continue. So between here and here, you can see there's kind of a bit of a growth of electrons. Right, to help us define what's actually happening, we look at something called the first ionization coefficient. We say that alpha dx electrons are produced by a single electron moving dx. So it's not one electron being released in dx, it's multiple electrons because of any subsequent reactions between the released electrons and that other molecule. So if n alpha dx electrons are produced by n electrons moving dx. If we move down a little bit, we can do some math around that, and we could look at, say, this whole region of 0 to x. We could integrate that n alpha dx, and all of a sudden you can see across x we've got n naught e to the alpha x. So that's an exponential growth of electrons. The movement of electrons is also related to time. T over here is time, it is not temperature. So the movement of electrons, you will know from physics as well, is basically a current. So alpha itself, it's dependent on pressure, temperature, electric field, and it differs with each type of gas. As such, the way electrons grow in a gas is dependent on pressure, electric field, temperature. Right, photoemission and photoionization. That's similar to what we spoke about with Bohr's model, where some sort of energy, photons, radiation can excite a molecule, or it can even have enough energy to ionize the molecule. We have something called attachment. Electronegative gases such as SF6 and O2 have the ability to attach electrons. So if we have a free electron in a gas, it'll attach to a molecule and it'll leave us with a negative ion. So if we have n electrons in a gas with an electric field and it moves through dx, it'll produce n-1 electrons. We define the attachment by the attachment coefficient, and we basically give a definition over here. Right, so we've looked at two processes that are important, ionization and attachment. I'm going to go back a little bit. Right, I spoke about these two values here. So the minimum energy to cause ionization in nitrogen is 15.5 electron volts for N2 and 15.32 electron volts for SF6. So that appears just from the ionization perspective that N2 is better, but N2 doesn't attach electrons. SF6 strongly attaches electrons. So there will be less electrons reaching that 15.32 electron volts. So that's why it makes it a better insulation gas than N2. Right, I think we'll call it there today. I'll recap ionization and attachment and start talking about the curves relating them to electric field and pressure in the next lecture. Are there any questions about that?